Today we're going to talk about electronic power systems in terms of solar panels and batteries, and basically that system that comes together. So here's an electronic power system example. So we start off with solar panels, and that brings in the energy, and then we have some sort of a regulation system which basically will take the solar power and turn it into battery power. So that regulation system controls basically how much current and everything is coming into the batteries and stuff. Then once you get some power into the batteries, then those batteries are typically used for powering things during the night or whatever, whenever the sun is not available. And that goes through what's called a DC to DC voltage regulator, and there's some efficiency in there. And that basically takes the battery voltage and turns it into the voltages that you really want. So let's talk about the different aspects of the power system. So first, let's talk about the solar panels. Solar power is often used to meet the needs of remote systems because it's basically inexpensive, lightweight, and it's relatively easy to implement. You can buy kits for very inexpensive at your local hardware store and start using solar power almost right away. It's very easy to actually use at this point. There are some weaknesses of solar panels, though. First, the panels must face the sun, and so if you're in a place where there's lots of trees, like my house right now is completely shaded with trees, and so I can't implement solar panels at my house, which sucks. Nighttime is also a bad thing in terms of solar power because, there's no sun during the night. And you often need batteries in order to store the energy for use when solar power is not available. So you can't just get solar panels, you need to have battery banks too. So it's sort of a combination system. Okay, let's look at an example of solar panels. You can go on to homedepot.com right now if you want and buy a bunch of solar panels, and you could set them up at your house if you wanted to. And what could you actually get, and how many panels would you actually need? Well, so ground-based solar panels are less than 20% efficiency, which means that of the amount of energy that's coming in from the sun, you can harness about 20% of that energy. Not great, but relatively speaking, solar panels are pretty cheap, and so you just buy more of them. The first panel that I looked at on homedepot.com, it's about 17.4% efficient. And in full sunlight, you get about 100 watts. It's made out of polycrystalline silicon, and it costs about $93. And so I looked at my last DTE energy bill, and I used 384 kilowatt hours in the month. And that assumes, if I make an assumption that I use energy about 8 hours per day, and that's about it, and there are about 28 days in the month, then I used an average of about 1,714 watts watts continuous across that time. That's actually a lot of energy. That's a lot of energy. Yeah, that's a lot of energy. So I would need about 17 panels for the peak time tracking of the sun. So basically, if I had all 17 panels pointed at the sun all throughout the day for 8 hours, that would work. But the problem is that you get roughly a 50% cosine loss, which I'll discuss during the day. And so you need to double the number of solar panels to about 34. And then there's also loss in the charging system, which is about 20%. And so you take the 34 and you add 20% to that, and you're ending up with about 43 panels. So if I had no clouds and no trees where I live, I would need about 43 panels, and then I could basically survive. And then I would need a bunch of batteries to actually store that energy. So let's talk about this thing called cosine loss. Well, most solar panels are in a fixed direction. So you basically point them at the sun at noon. All right. And so when the sun rises, it doesn't shine on the panels because it's at sort of an oblique angle. So you have the solar panels here and the sun is over here. So it's shining this way, not shining down on the panels. But during the day, the sun shines more and more and more on the panels until it gets to about noon. And then it shines less and less and less until it's at sunset. And then it's once again not shining on it. And so you can basically make what's called a cosine curve, which is, so if midnight is here and this is dawn, you get no energy throughout that time, and then the energy goes up throughout the day, and then it comes down. And then at dusk, you have no energy again. Dusk. And this is midnight again. And this is your peak energy. And if you take the area of this, or you find sort of the average value, it's roughly 50%. Roughly 50% of your peak. Okay, and so that is what we use as a rule of thumb, is that if you're sitting, in one fixed location and you point it at the sun at noon, you roughly get 50% of the energy, total available energy throughout the day, if you don't change the direction of your panels. Okay, but there are seasons on Earth, which, in some ways is nice, in some ways sort of sucks. For solar panels, it sort of sucks because the sun comes in at different angles. So if you're looking on like March 21st, which is equinox, Ann Arbor is sitting up here. It's at 42 degrees latitude. And if you were to put the panels flat to the Earth like this, then the sunlight would come in at an angle of about 42 degrees. And so what you need to do is, if you are actually wanting to get the optimum amount of energy coming in, then you would tilt your solar panels by about 42 degrees. 42 degrees there. And that way the sunlight is coming in exactly perpendicular to your solar panels at noon, and you're getting the most optimum amount of energy coming in. But then what happens? Then winter happens. So if you have your sunlight coming in here at 42 degrees, then you actually have, if you have your panels tilted at about 42 degrees, then you have sunlight coming in here, and then you once again get an angle between the solar panels and the sunlight. And this tilt here is about 23.5 degrees. 23.5 degrees, because that's about the tilt of the equatorial plane of the Earth with respect to the sun. And so 23.5 degrees, and so you're getting an angle here of roughly 23.5 degrees. Oops, I keep doing that. 23.5 degrees. So what you can do in the winter is then you can change the tilt of your solar panels, and you can, raise them up a little bit more here, and you can make this angle 42 degrees plus 23.5 degrees, which is equal to 65.5 degrees. And that is the peak for the winter solstice. A lot of people end up just leaving their solar panels at the equinox conditions, but you can tilt them up a little bit more if you wanted to. And then if you wanted to tilt them, let's say that this is now summer conditions, and you have 42 degrees once again, then the sunlight comes in here, and it's 23 degrees, 23.5 degrees in the other way. And so now what you want to do is you actually want to tilt your solar panels the opposite way. And so you want to have them tilted like this. So this angle is now 42 minus 23.5 degrees. And so that is optimum for summer conditions. So if you had a perfect design for a solar panel system or you had an optimal design for a solar panel system, the solar panels would go from being about 18.5 degrees in the summer to about 65.5 degrees in the winter. And it would just sort of slowly rotate back and forth from summer to winter and summer to winter. Most systems are not like that. And so most systems just sit at like 42 degrees. And in the summer, they're less efficient by the cosine of 23 degrees. And in the in the winter, they're less efficient by the cosine of 23.5 degrees. And in the summer, they're less efficient by 23.5 degrees also. And so you just sort of suffer with those losses. You just build the system big enough that it can handle those losses. All right, so solar panels for space encounter this exact type of cosine loss also, but it's much worse, and I'll go into that in just a second. Space-based solar cells are around 27 to 30% efficient, so they're significantly higher than efficiency down here on the ground. One of the reasons for that is because you want as little mass up in space as physically possible. And so you don't want a whole bunch of panels. You want just the right number of panels. So you buy the most expensive, the highest efficiency cells to bring the mass of the satellite down. The problem with that is that cells cost about 500 per cell, which gets you about 1 watt of power, which is pretty insane. Then if you need to put cover glass and a diode on them, which you do need, but I'm not going to talk about that, it costs another $500-ish. And then if you want to put them on a board to actually send them into space, it costs about $1,000 to do that. So to put one cell into space costs about $2,000, and that gets you about 1 watt. So if you wanted a 100 watt panel, it would cost you approximately $200,000 for 100 watts of solar power on a satellite. That's a lot of money. That's a lot of money. Space is expensive. These are what are called triple junction cell. They're very high efficiency. And basically the reason that they're called triple junction cells is because there are 3 layers of solar cell or cells. So one layer absorbs one type of wavelength, the next layer absorbs a different type of wavelength, and a third layer absorbs a third type of wavelength. And each of those adds a little bit more to the efficiency. All right, let's talk about cosine losses. So you have a satellite that's orbiting in space. Satellites don't stay still. So how do you get enough power with a cosine loss? Well, it depends very, very, very much on the orbit. And so let's talk about that on this page here. So let's say that you have a satellite here, and it's got solar panels that are sticking off the back here, and they're laid out like this, basically. If the satellite is going around the Earth like this, you can see that the solar panels are not getting any energy here. There's no energy coming into the solar panel. But let's say that the satellite moves this way and it's rotating. Here it's actually in full sunlight. And then when it gets over here, it's pointed this way. And there it's not getting any no solar coming in that direction. So it's getting lots of sunlight here, lots here, none here, none here. And this is in the nighttime, so there's no sunlight, and so there's no solar here. So you can see that you're actually only getting sunlight basically in this region here. And so you have to have really big solar panels because you're collecting all of your sunlight energy here, and then you're using the batteries throughout this entire time of your orbit. So you need really big batteries and you need big solar panels. for a satellite that's orbiting like in this type of orbit plane. There are other orbit planes where it's much, much better, but this is a demonstration of sort of the worst case satellite orbit here. Okay, so you basically need to bring in more energy than the system uses over a cycle, like an orbit. So you need to bring in a lot of energy here, and you're going to use it in all the rest of the spots. So for a home, that's probably a day, and for a satellite, that's an orbit. You need to consider worst case scenarios. So for a house, that would be like cloudy days. Like some days you're just not going to get very much solar panel or solar energy. For a satellite, you're going to go the longest eclipse orbits with the worst geometry for viewing of the sun. And so you take that into account. And then you consider losses in the system, which we'll talk about in a little bit. And then you compare the net input of your system with the net output of your system. And then you see if you're going to get the amount of energy that you need. If you plan for the worst case scenario, but you're actually in the best case scenario, you get a huge amount of excess energy into your system, which basically is heat. And so you may have a lot of excess solar energy coming in. And that's why when you're at home, you can sell that energy to the grid sometimes. If you just have a battery system, then you're basically just wasting that energy. But if you have what's called a grid-tied system, you can sell that energy back to the power companies. And that's actually a really good thing to do. On a satellite, you're just sort of wasting that energy, and that energy actually goes into heat, and it heats up the satellite, and so then you have to figure out how to get rid of that excess heat. In the worst case scenario is often when you have very little sunlight, and so you're not getting very much energy in, and that's when you need heaters because you have the least amount of energy coming in, and that's the worst time to use heaters because you don't have very much energy that you can use. It's really dicey trying to figure out the energy budget for a satellite. We're going to skip this. Let's talk about power regulation systems. Really all I want to do here is talk about peak power trackers. So a solar cell works by basically having sunlight knocking an electron off of a silicon atom. And then if that electron is just knocked off and it doesn't go anywhere, and so you need to apply some sort of a potential, a voltage across it, and then you actually get a current that flows. So there's a relationship between the potential applied and the resulting current that you get. And power is equal to voltage times current. So power is equal to voltage times current, which is I. Okay, so that's a key equation here. So your goal isn't to maximize current. It's not to maximize voltage, it's to maximize power. You want to get the most power out of the system that you possibly can. So what you do is you turn up the voltage until the current actually starts to decrease. But there's a point where the power is then maximized. So if you look at this plot over here, what you have is you have voltage that is plotted against current here. And what happens, this is a solar cell here, and let's say that you're sitting on this, you're sitting on this line. All right, so this line is very dependent on like temperature, it's dependent on angle of incidence of the sunlight, it's dependent on lots and lots of different things, cloudiness in the sky, all sorts of crap. And so what happens is that what a peak power tracker does is it basically sweeps through voltage. So it increases the voltage here until the current starts to decrease, and then it tries to figure out where you get the peak power. So remember that power is equal to voltage times current. So back over here, you have too little voltage and some current, and so you're getting very low power. Over here, you're getting high voltage, but low current, and so you have low power also. And so it is in this region here where your power is actually peak. And so the peak power tracker basically goes up to the point where the current starts to decrease, and then it goes back and forth in this region until it finds the peak power. And let's say a cloud goes over the solar panel, and then what happens is that you jump down to, say, this curve, and then the whole cycle starts again, and it starts to increase until it finds the current starting to decrease, and then it cycles back and forth until it finds the peak power. And so your peak power tracker basically keeps track of the proper voltage to run the system at to get the right amount of current to maximize the right amount of power coming into the system. And that's what happens. Let's talk about batteries. So batteries are one of the only effective ways to store energy on a satellite or in a remote system. We're going to ignore RTGs. We talked about them in another presentation, but we'll skip those. Batteries are relatively cheap. They're relatively easy to use, and they're very, 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 very available now because cell phones and power tools and all sorts of stuff like that. You can buy batteries all over the place. They're super cheap now. The problem is that they're pretty heavy. For a satellite system, they're very heavy. For a car, they're extremely heavy. So I actually was just watching a video on some nice Porsche. There's a Porsche electric Porsche vehicle, and the Porsche is 5,000 pounds, which is an extremely heavy sports car. It's got good performance because they put really big motors and everything in it, but the reason that it's 5,000 pounds is because of batteries. Batteries are very, very heavy. There's also a strict temperature range. So what happens when it gets cold is that you lose storage capacity, which is not good. And then if it gets too hot, some batteries can actually catch on fire. So that's actually pretty bad too. So you have to watch out for this temperature range, and you need heating systems and cooling systems for the batteries. So that's not so good. And then there's a limited lifetime of a battery. You can only charge it and discharge it a number of times. So we'll talk about that. There are different kinds of rechargeable batteries. There's nickel metal hydride, and there's lithium ion. There's also other types, but those are the two main ones that you'll run into at like Lowe's or Home Depot or something. The life of a battery is dependent on the number of charge and discharge cycles. And even more detailed than that, it's actually dependent on how deep you charge the battery or discharge the battery and then charge it back up and then discharge it again. And so the depth of discharge is actually quite important in determining the life of a battery. So the depth of discharge is how much you drain a battery before you charge it again. So if you discharge it like 25%, that means that you're only discharging it down to about a 75% state of charge. So you're only using about 25% of the energy, and then you put that energy back in. Okay, so people have done tests to basically look at the number of cycles that you can get out of a battery versus the depth of discharge here. So the cycles, number of cycles, is basically how many times you can discharge, charge, discharge, charge, discharge, charge. All right, so if you look at how these two things are related, if you discharge something to 100% discharge, so you use all of the power inside the battery, and then you charge it, you discharge it all the way, you charge it again, you're only going to get 500 cycles for some random battery. This is just a random battery. It's meant to be an example. But let's say instead you actually discharge it only to 30%, and then you charge it. 30%, charge it. 30%, charge it. Then what happens is that you might get 2,050 charges and discharges. Okay, so why does this matter? Well, if you have a phone that you're trying to like maximize the lifetime of, you don't want to necessarily drain it all the way down and then bring it back up, all the way down, bring it back up. If you do that like once a day, it was only going to last maybe 2 years. And so that's not actually good. But if you actually discharge it only 30% and then you charge it again, then you're going to get 2,050 charges and discharges from that. So maybe you have to do that twice a day as opposed to once a day over here. Still, the lifetime of the battery is going to be twice as long. All right. So this really matters because it depends on where you actually are going to deploy your battery system, your system. If you're deploying it in space, then what you really want is you want to move up this part of the curve here because you're going to get 15 charge discharge cycles per day. And so, you know, if you go 3,000 here, you divide that by 3,300, you divide that by 15 charge discharges per day. That means that you're only going to last for, let's see if I can do math, 220 days. All right, that's not great. That's less than a year. And so actually you want to have even less discharge than say 20% if you're on a satellite, because you are not able to replace the battery. If you're, you know, at your backyard, then it doesn't really matter if you have to replace the battery once a year or once every other year or something like that. So it doesn't necessarily matter. You can go all the way down into this region and you can discharge the battery a lot. It all depends on how easy it is to discharge, or I'm sorry, replace the battery. Okay, so let's talk a little bit about voltage regulation. So basically your battery is going to have some sort of voltage and you want to regulate it to some other types of voltage. So a voltage regulator is basically that you have a system that outputs voltage at a certain level. Let's say that you have a battery that is outputting at say 7.4 volts. All right, but then you want to have some sensors and stuff like that that are coming in at like 3.3 volts. Well, so you need to regulate the power from 7.4 volts down to 3.3 volts. How do you do that? Well, one of the ways, I think you talked about this in lab, is with a voltage divider. A voltage divider is where you put two resistors in series like this, and then you divide the voltage here. So basically the voltage, because these two resistors are equal to each other, the voltage V out is going to be 1/2 of V1, which is going to be equal to 5 volts, which is fantastic. So if you wanted to go down to 5 volts, say you want to power some sort of an Arduino that is a 5-volt Arduino, this would be a perfect system. But then what happens if your battery voltage isn't exactly 10 volts? So if your battery is 9 volts instead, it drops in voltage just a tiny bit. Now V out is going to be equal to 4.5 volts, which the Arduino is not going to like at all. And so a voltage divider is, you know, relatively simple and everything, but it really sort of sucks as a voltage regulator. So what we use instead is what's called a Zener diode. A Zener diode does something really interesting, which is that it cuts off the voltage. All right, this is their Zener diode here, and this is an oscillating voltage. So the voltage is going from some low voltage to some high voltage here. All right, oops, actually it's going to some high voltage here. Okay, and so what's happening is you're taking the voltage from here to here, And what you see is that the voltage is going up for a little bit. Instead of going all the way up to the high voltage, it actually is cutting off at this certain voltage. And the Zener diode here is basically limiting that voltage to stop at that certain voltage. And then this oscillating voltage is coming back down, and it comes back up, it stops there, and then it comes back down. And so a Zener diode is limiting the voltage so it won't go above a certain level. Now, the really cool thing is that what we can do instead of working down in this range here, what we can do is always put in a V greater than VZ. So if V, the voltage, is always greater than VZ of the Zener diode, then we'll always get that V is going to be equal, or the output voltage is going to be equal to VZ. Okay, so that is clipping there. So what happens is that we put in some sort of a voltage, V1, that is always greater than the Zener diode voltage, and then we get out this V2, which we can set to 5 volts if we want. We can buy a Zener diode with 5 volts or a Zener diode with 3.3 volts, and we can get that voltage out. As long as V1 is always greater than 5 volts or 3.3 volts, we can get that out of the system. And so a Zener diode is a good way of actually regulating the voltage on the system. All right, so that is basically the conclusion of this. We use solar panels for collecting energy. They're relatively cheap and easy to implement. There are cosine losses, which means that you usually need to have a much bigger system than you would if the solar panels were pointed at the sun all of the time. And so it's somewhat complicated to size those, but it can be done. There's a peak power tracker, which basically figures out the maximum amount of power at any time by playing with the voltage. And the reason that it does that is because you have a dynamically changing environment. Like the sun is not always shining on your panels exactly the same way. The temperature is not always exactly the same. You have clouds coming across it. You might have some snow. You could have all sorts of different conditions. And so the peak power tracker actually dynamically changes the voltage that it's putting across the panels in order to maximize the power. You use batteries for storing energy during non-sun times, and the depth of discharge needs to be monitored, or you need to size the batteries just right to make it so the depth of discharge allows you to get the lifetime that you need out of the battery. And then with power regulation, you use power regulation to take your battery voltage and convert that to the voltages that you actually need. And Zener diodes are really a good way to actually do that. So that's it. Thank you very much.